Hey guys, my name is Adil Qureshi, and I'm going to be doing this switching problem for you guys. It's from exam 2, it's question 2 from that exam, and the main thing about these switching problems is you have to analyze each time period of the circuit, alright? But we'll go through it and it'll make sense. Alright, so let's first read it. The circuit shown below has one switch, S1 right here. That's that switch right there. Alright? It has been in position A for a long time. Long time. Alright? What long time tells you is at that time period, which would be t is less than 0, that means that all capacitors turn into an open circuit and all inductors turn into a short circuit. That's what steady state is, the long time. Alright? So let's analyze that time period. I already drew it, right? And you might notice that the right side's not there anymore. And that's because it's not relevant to the inductor system at that time period because it's not connected to it. All right, so let's analyze this. All right, you can see this is a short circuit now. So the voltage across that short circuit is going to be equal to 0 volts because it's just like a wire. There's no potential difference across it. Now IL of 0 minus, right, 0 minus being before 0, it's going to be V equals IR, right? You can use that. And if you manipulate, it's just V over R, right? And the V is 10 volts, and the R is 1 ohm, right? That I right there. So that's going to be equal to 10 amps. And something notable is that IL of 0 minus is also equal to IL of 0. It's also equal to IL of 0 plus because current in an inductor cannot change instantaneously, and vice versa for a capacitor, but it's voltage, right? Voltage in a capacitor can't change instantaneously. Okay, now let's look at the next thing. At t equals 0, S1 moves from position A to B. Please find the inductor current, IL of t, for t is greater than 0. Okay, so that would mean that the switch moves there. And this is not relevant to the system because that's not connected to the circuit. So let's analyze that portion. Right, here's that portion. And what I actually like to do, because this is the last time period, switch, this is the last switch that happens, we have one more time period that you might not think about. T is equal to infinity when it is like that for a long time. Now, I like to analyze this because it makes the equation easier. And we're going to have to analyze it anyways. So that'll make this inductor short. And what's really interesting, actually, you can look at the circuit and you can already know the answer. All right, IL of infinity is going to be equal to 0 amps. And let me explain why. It's because there's actually no independent source connected to this circuit at all. There's no battery. There's no current source. You can do a node voltage. That's completely fine. But yeah, there is nothing connected here. So there's actually no point in doing that. You could, but I'm not going to do it because there's nothing supplying it. So it's going to be 0. All right. Now, the way we get this IL of t equation is we're going to have to reference this chart. Right? IL of t, all right? This is the formula sheet that we have, and that's the step response of an inductor. All right, so using that equation, we have this, which would be 0. In this case, that's when the switch happened. We have this, but the one thing we don't have is that tau. Okay, now you're going to be wondering, how do we get that tau? Well, we're looking at this circuit now, this circuit in time, and tau is defined as L over R for inductor circuit, right? Now, we have L, that's 8.65, but we don't have R, REQ to be specific, the resistance that this inductor sees or experiences. So you would think maybe we could just simplify all these resistors. This resistor, you think we could simplify it. But we actually can't because there's these two dependent sources. And that means we're going to have to do a test method, right? So we will remove this inductor because it's what the inductor is seeing. And we will analyze what the resistance is. Let's move this. I'll make this small. Okay. So I like to do test source method. You can do test I like to do test voltage method, but you can do test source. Right, so I'm gonna label this as IT. Right, and let's start doing this. Right, we're gonna label this as VA because that's plus minus, that's VA. Okay. I think, yeah, okay. Let's do some node voltage because I like to do node voltage. So let's do that VA node. Okay, VA over 10 kilo ohms. All right, that's that current right there. Plus VA minus 5 VA because it's a voltage drop right here. And that's going to be over 2.2 kilo ohms. Plus, this is opposing, so it's actually going to be negative. Negative 25 millisiemens. VB. And negative IT because it's also going the other way. Okay. Now we need two more equations because we have three variables in this equation. So we can get IT pretty simply. 1 volt here, and VA is defined here. So IT will be 1 volt minus VA over that resistor, 5.6 kilo ohms. Yeah, and last variable, we need VB, right? And we can solve this very similarly, right? V equals IR, we know the current going through it, I, we know the resistance, 5.6 kilo ohms, and we are just solving for VB. But one important thing, I is going into the negative terminal of this voltage, so active sign convention is going to make this actually negative. Negative IT, 5.6 kilo ohms. Okay, now that you have these three equations, okay, so now you have these three equations, so we're gonna have to solve, we want to solve for IT. And the way I'm going to do that is I'm going to take my calculator, I have the TI Inspire CX2 CAS, do menu, 3, which is algebra, 7, which is solve system of equations. And I'm going to plug these three in, and I'm going to get IT is equal to 1.156 times 10 to the negative 5 amps. Okay, but we actually want REQ, and that's VT over IT. We set our VT to 1 volt. That was our test voltage. All right, so 1 volt over this. Put that in a calculator, or maybe you can solve it. I don't know. 86.5 kilo ohms is our REQ. But the thing we need for our actual equation is tau, which is L over R for this instance. We know L is 8.65 henries, and we just calculated for R. REQ I should have put here. Tau is equal to 0.1 milliseconds. All right, now we have everything. All right, we can solve for our final equation. All right, IL of t is what it's asking for, and this is for t is greater than or equal to 0. All right, so let's go element by element. IL of infinity, we solve for that, that's 0. All right, this t naught right here, that's just the same as when the switch happened. That was at 0 seconds. So IL of 0, we solved that to be 10 amps. All right, so 10 amps. All right, we already said this is 0. So 10 amps, E negative t over tau, which is 0.1 milliseconds. And this is our final answer. Thank you guys. Hope you enjoyed.